Okay, Jack from Smoky Mountain Scientific here, and today I want to talk a little bit about op-amp circuits. Okay, and an op-amp, it has this symbol. It has an input, a non-inverting input, and an inverting input, an output, and it's got a high voltage, and by high I mean higher than low voltage. Okay, so this is, in my case, usually going to be 3.3 volts, and the low voltage, the down voltage, is going to be ground. Okay, so the output that we have is going to be constrained to be between those two voltages, right? That's the max and minimum. And for an op-amp, the output, V output, is going to be equal to a constant times the difference between the input voltages, the non-inverting voltage minus the inverting voltage. Okay. All right. So that being the case, if we constrain this between 3.3 and ground, what is the output as a function of the input? V plus minus V minus. Okay, so it can't go below ground, can't go above 3.3, and that means we have some theoretical behavior where this C, the slope of this line is C, and then we have the real behavior, which is limited by the input power inputs. Okay, now this is theoretical, but C for reasonable purposes is very large, and this is going to, in practice, get on the screen. In practice, it's going to look like it jumps straight up like that. Okay, so we are limited between our input, our inputs to the power pins, and it's going to look pretty steep, the slope of that. Now, that being said, we can make circuits that have feedback, and the simplest feedback circuit is one where we have our input voltage and we have our outputs tied together. We have our output tied to our V minus, right? And what this is going to do is if V plus is larger than this down here, then it's going to output voltage and bring it into line with V plus. All right, so this circuit is called a voltage follower. And we're going to have the input voltage come to the minus sign, and the output voltage will equal the input to the positive non-inverting side. Okay, so you're just getting out what you put in, and the question has to be, why would you do that, right? If you're just getting out what you put in, there doesn't seem to be a real reason for doing that. But for our spectrometer, we have a charge-coupled device, and the charge-coupled device puts a voltage onto a very small capacitor, right? And when we attach this to some circuit out here, then this circuit will probably have input voltages, and it'll have an internal capacitance, right? And if this internal capacitance is larger than the capacitance of our voltage source, then we are looking at affecting the voltage of our capacitor that we're trying to measure the voltage on, and that's not good, right? So what we want to do is take our little capacitor that's been charged up by our CCD and put that to our voltage follower. Okay, so this means that the voltage here is going to be output here, and that's what we get. and it's not affected by other things in the circuit. Well, it won't be affected. All right, that is the voltage follower. We have another circuit that we're not going to use in the spectrometer, but I figure I'll tell it to you anyway, and that is the current follower. Current follower. Okay, current follower we use a lot in our, well, we use a lot. We use in our what's it called? Potentiostat. All right, so a current follower has a reference voltage, let's call that Vref, attached to the positive non-inverting side, and we're going to put a current through this resistor down here, and we're going to measure the output over here, right? And as we said, this is a feedback loop, so we're going to end up with the voltage at this point being our Vref, okay? And if that's the case, then the current through this resistor will result in a drop in the voltage, and therefore the voltage here, Vref minus Vout, will be equal to the current that flows times the resistance. Okay, so this makes it a straightforward way to measure the current that is coming from some current source. So I is equal to Vref minus Vout divided by R. Okay, all right, so there's the voltage follower and the current follower, and we also will have to talk about general inverting amplifiers. Inverting amplification. All right, an inverting amplification circuit looks like this. We have some reference voltage that we attach to our positive non-inverting pin. We have some, well, we have a resistor here. We'll call that R1. We have a resistor down here. We'll call that R2. And that's how the circuit goes. Okay, so we have a voltage, let's call that V minus here, and we have a V out. All right, now if the reference voltage since we have a feedback loop, we have a reference voltage there, and that means that V minus minus reference, V minus minus reference is what? Oh, okay. So we have a current that flows through both of these resistors. It can go one way or it can go the other way. And then the current that flows through R1 is V over R1. And the current that flows through R2 is the reference voltage, minus V out divided by R2. Okay, so these two things being equal, you don't pass any current through the input pins here, so these must be equal because the current here, I1, is equal to the current down there, I2. And that means that you can calculate the output based on an input. Okay, so let's see. V out is going to equal ref plus R2 over R1 times ref minus V minus. Okay, so those are three common little amplifier circuits, and you should probably be familiar with them, or at least have seen them. The only other thing I want to talk about today is, let's see, PWM signals and low pass filters. All right, so you probably know what a PWM signal is. It is what you get if you say analog right, and I believe it's a lowercase a, but that's okay, on an Arduino, and you give it a pin number and a value. Okay, and what that does is it sets up a PWM signal, and the PWM signal is a square wave. The square wave goes from your maximum voltage, which in my case is 3.3, to the low voltage, which in my case is ground, and it has a certain period and it has a certain amount of on time, right? So the period is that far, and the thing called the duty cycle is this much, right? So the deal is that this thing looks like an analog voltage. Analog voltage, all right? It looks like an analog voltage on a slow time scale. If this is half the time up and half the time down, then it looks like this voltage. But it's really not this voltage, but we can convert it to that voltage, all right? And the way we do that is with a low-pass filter. So if we take a PWM pin and attach it to a resistor and then a capacitor and ground that into the capacitor, and now we have a voltage out, okay? And the deal is that it takes some current to pass through this resistor to charge up this capacitor. And once you charge that capacitor, if you turn off the PWM for a small period of time, then that voltage is maintained for a period. It drops off like this. But if you have a fast enough PWM and a large enough capacitor and a large enough resistor, then you can come up with a very analog type looking signal. And that's what we're going to be doing. All right, so those are the circuits that I wanted to tell you about, and that's it for now.